In front of you, you see a typical linear programming problem. It consists of basically two parts. The first part is the objective function. You'll usually see wording like minimize or maximize, and then you'll see some formula that is the formula you're trying to minimize or maximize. In this case, it says minimize z equals 5x plus 2y. Now, if you think about it, as x and y get bigger and bigger, this function's going to get larger and larger. As x and y get smaller and smaller, and perhaps become negative, it's going to get smaller and smaller. So if that's the only thing I have, there really isn't a minimum to this because it can get as small as I want. If I put in negative 1 million for both x and y, that's going to be a really, really small value for z. That's why you have constraints. Constraints are a system of linear inequalities. In this case, 2x plus 3y greater than or equal to 6, 4x plus y greater than or equal to 6, x is greater than or equal to 0, and y is greater than or equal to 0. These constraints define a feasible region, and over that feasible region, we're hoping that we'll be able to find an x and a y that lead to a minimum value for the objective function. As a part of these constraints, we have the non-negativity constraints. These are pretty typical for most linear programming problems because most of the time the variables represent numbers of items, and your numbers of items are not going to be negative. That's why we call them non-negativity constraints. So what our goal is to find the value in the feasible region that minimizes the objective function. So I've gone ahead and graphed out our feasible region here. And before we get going, let's make sure everything makes sense. First of all, we have our non-negativity constraints, which basically says that everything has to be positive. So everything here is in the first quadrant. I also have 2x plus 3y equals 6. And if I look carefully, if y is equal to 0, x is equal to 3. That's the point that I see down here. And if x is equal to 0, then y must be equal to 2. That's this other point. So if I were to take my red line and test the point 0, 0, so 2 times 0 plus 3 times 0 is not greater than or equal to 6, that tells me I have to be shading everything on the other side of the line. And since the red line is that first inequality, the blue line must be the second one. So if I test 0, 0 in there, I get 0 plus 0 greater than or equal to 6. That's also false, so that means that I have to be shading on the right-hand side of the blue line and also the right-hand side of the red line. Now let's get an idea of what's going on with this objective function. I'm going to go ahead and put a value of z into the objective function. So I'm going to put 20 in place of z. So when I graph this, I get a line, and what this means is everywhere along this black line, z has a value of 20. And obviously, that's probably not the optimum value here. So let me try another value. So now let me put in 15. All along this line, I get a value of z equal 15, and you'll notice that it's parallel to the previous one and to the left. Let me do one more. I get another parallel line, and what you'll notice is z equals 20 was here, 15 was here, 10 was farther to the left, so the observation I might make here is, as z drops, the line moves farther to the left. Is it clear that the lowest that z can be will occur at the corner point that's right here? And it's probably going to be a z value, it looks like something like 7, 8, or 9, right in that range. But if I go any farther than that, I'll get lower z values, but I won't be in the feasible region anymore. So let's go ahead and find the corner point. So the corner point that we're looking for is the intersection between 2x plus 3y equals 6 and 4x plus y equals 6. So I'm going to do this by elimination. So I'm going to choose to eliminate the x's. So I'm going to multiply the top equation by -2 to get -4x minus 6y equals -12. And I'm going to add that to 4x plus y equals 6. My x's go away, and I'm left with minus 5y equals -6, which means my y value has to be 6/5. Now that's about 1.2, and if I look at the point of intersection there, 1.2 looks reasonable. So now I'll go ahead and put that y value of 6/5 into the second equation. And when I subtract 6/5 from both sides, I get 4x equals 24/5. And when I divide both sides by 4, I get x equals 6/5. And an x value of 6/5 or 1.2 also looks reasonable for this point of intersection. One of the things I always do is when I find a value, I make sure that it makes sense with the graph that I already have. So that puts my corner point at 6/5, 6/5. I know that that's my optimum value, but what I'd like to know is what's the z-value that corresponds to that. So I'm going to go ahead and put 6/5 in for x and y in my objective function. And when I do that, I get 5 times 6/5 plus 2 times 6/5. And so let's see, that'll be 30/5 plus 12/5 gives me 42/5. So that's a value of a little bit bigger than 8, which is consistent with what we came up with before. So that is the lowest that z can be on that region. If I went any lower, I'd be outside of the region. What this leads me to is the corner point theorem. And the corner point theorem says that if an optimum value, either a maximum or a minimum, of the objective function exists, it will occur at one or more of the corner points of the feasible region.